there. So he moved up to San Francisco to do a bachelor's degree at Berkeley, and then to MIT for his PhD, where he worked on aging of aerosol, and he's going to talk about some of that work today. I'm not sure if you're going to talk about this or not, but you did a lot of work at Lyrex also, sort of, where they were doing controlled burns, and Chris Kappa had some of those data in the fall. And then from MIT, he moved to Toronto almost exactly a year ago. Exactly today. It's middle of the year. Yeah, 1 year. So, and he's been. And he's been doing indoor chemistry, or motivated by chemistry motivated by indoor chemistry, and it's going to show a little bit of that today. I don't know if you're going to show the dartworks, but also sort of the growth of organic films indoors and studying of late. But I guess the cold weather of Toronto didn't entice him to stay, and so he's leaving very soon, unfortunately. Very good for him. He got a job in the South Coast Air Quality Management District, which is involved very much in air quality measurements and control in Southern California.
No, Andrea Polidori is research.
Yeah, and so we're unfortunately going to be losing Chris at the end of March and heading back to LA. Back to the war, exactly. And so with that said, I'd like to just.
Thanks, John, for the introduction. So today we're going to be talking about some of the work from my PhD, actually. So a lot of heterogeneous oxidation work, but also some heterogeneous oxidation work that I've been doing more recently here at U of T. Here's a brief outline. So for the outdoor aging portion of the talk that I did for my grad work, I'm going to be talking briefly about morphology and how that affects heterogeneous oxidation kinetics, and also about the products from heterogeneous oxidation. So I'm using a model organic aerosol here, falling to approximate aerosol. And then for the second part of the talk, I'll be talking briefly about some indoor aging studies. So we've been taking a look at third-hand cigarette smoke and the ozonolysis of that on indoor surfaces. So to start off with the outdoor perspective on things, when we think about organics in the atmosphere, we typically think about two major things. One is organic particulate matter or organic aerosol. We also think about volatile organic compounds. So some of these organic aerosols can be emitted directly from primary sources such as combustion from vehicles or biomass burning, and same thing with VOCs. But the organic particulate matter can also, sorry for the typo there, the organic particulate matter can also come from secondary sources. So these VOCs that are emitted from biogenic sources such as pine trees, so like alpha-pinene or isoprene, or anthropogenic sources, they can also get oxidized by radicals such as the hydroxyl radical, and this can lead to formation of lower levels of the species, which can then condense onto either pre-existing particles or form new particles, forming secondary organic aerosol. So there's been a lot of work done in this area, particularly laboratory experiments that look at the yields of various precursors, so alpha-pinene or isoprene for biogenic sources, or say toluene for anthropogenic sources under a wide variety of conditions, so low and high NOx conditions or different humidity levels. But when we take these emissions of POA and VOCs and input these yields from these laboratory experiments, chemical transport models still often cannot reproduce the exact loading or composition of the aerosol that we see in ambient measurements. And one of the big reasons for this is that these organics still remain reactive after they're emitted or formed in the atmosphere. And one thing that might be able to bridge the gap between what we observe in our measurements and what our models say should be happening is heterogeneous oxidation. So heterogeneous oxidation is one form of aging that happens in the atmosphere, and it is the direct reaction of hydroxyl radicals with molecules in the particulate phase. There are also other forms of aging such as photolysis or oligomerization that can also contribute. But for this talk, I'm really going to focus in on heterogeneous oxidation. So these heterogeneous oxidation processes, they could potentially lead, well, not too much is known about them because a lot of the work has been focused on this condensation and formation of SOA, but they could potentially lead to particles with modified chemical and physical properties as they age the aerosol. So one of the main questions that I had during my thesis work was, how does heterogeneous oxidation affect the loading and composition of organic aerosol? And when we think about heterogeneous oxidation in the atmosphere, we think of two very general reaction pathways. So this is just a very, very simplified version of the mechanism here. And when OH reacts with an organic molecule, you can get functionalization. So this would lead to the addition of oxygenated functional groups to the carbon backbone. This would lead to molecules with lower volatility, higher molecular weight, and addition of organic mass to the particle phase. The other major pathway that you can undergo is fragmentation. So here you're also adding more oxygenated groups to the molecule, but you're also getting carbon-carbon bond breakage. So in this case, you can actually lose mass from the particle phase. Now, when we look at previous heterogeneous oxidation studies, here I'm showing a plot of the average carbon oxidation state on the left. So this is just a metric for the composition of the aerosol. You can estimate this by 2 times the oxygen to carbon ratio minus the hydrogen to carbon ratio. And on the x-axis here is the number of carbons. So higher number of carbons on the left, and then decreasing to lower number of carbons on the right. And then each one of these separate colored lines, this is a separate heterogeneous oxidation flow tube study. So these were done in collaboration between Jesse Kroll's group at MIT and Kevin Wilson's group at LBNL at Berkeley. And for each of these different oxidation studies, we can see some general trends. So if we take a look at squalane, for example, so squalane is a C30 saturated hydrocarbon, so C30H62. We start at a carbon number of 30, and the oxidation state, 2 times O to C minus H to C, is about -2. There's some weird reprint of the graphic here, so ignore these small little black lines. And as we oxidize these particles in the flow tube, you see that the carbon number drops, and then slowly the oxidation state increases. And then we can take a look at all the different precursors, and based on the initial composition of that molecule, it starts at a different spot on this graph, but generally they all move in the same direction. So they're all moving to the right and up towards this corner. So each of these studies is a particularly unique molecule and not necessarily representative of ambient organic aerosol. So, and also what this previous slide doesn't say anything about is how fast these changes take place. So what we really want to know is over what time scales do we see these changes happen? Because if they happen over the courses of days to weeks, then we might want to care about them and actually input them into our models. But if they take place over the course of, say, years, then they're not really relevant for the atmosphere. So what we can do is actually take the combination of all these studies, and instead of plotting them in this O to C versus carbon number space, plot them against OH exposure. So OH exposure is just the OH concentration times time, and that gives you a metric for how long this aging process is happening. So when we take all the data, plot it against OH exposure, and then we can fit all of that data, we come up with these fairly simple parameterizations. So for the change in carbon oxidation state, we see that over about, this is over 2 weeks, but over about a week of time, the OSC change is about 0.6. And then on the right-hand side, I'm showing the fraction of carbon remaining in the particles. And when we look at that, over about a week, we are seeing about 10% loss of carbon mass. And this is all assuming an uptake coefficient of 1, meaning that every time a hydroxyl radical hits the particle or molecule in the particle phase, it's giving you a reaction. And generally, for a lot of these heterogeneous oxidation studies, we see uptake coefficients of around 0.1 to 1, and sometimes even higher if you're getting secondary chemistry happening in the particle phase. Okay, so for one big simplification in all of these studies is that they're all done on single component aerosols and flow tubes. And we know that ambient particulate matter is very complex and consists of many different organic compounds. And one of the questions that I had in my thesis was, how do phase and morphology affect heterogeneous oxidation kinetics? So all of the previous compounds, previous experiments kind of implicitly assume that these particles are spherical and well mixed. So we're using an aerosol mass spectrometer to measure the composition for all of these studies. And that basically gives you the average composition of all the particles. So it doesn't really say anything about how the composition might be different on the surface versus the interior, or if the different particles may have different compositions. And one thing that we know about ambient particle morphology is that it can be very complex. So what I'm showing here on the right is just the compilation of TEM images from this paper in 2012, showing TEM images of particles collected in Shanghai. So as you can see, none of these are perfectly uniform spherical particles. On the top row, we can see some particles that have inorganic cores, and they've identified some organic coatings on the outsides of these particles. Down here in the bottom left-hand corner, you see kind of like an agglomerated soot particle with different OC and inorganic rich domains, and then all sorts of shapes inside this in between with different organic and inorganic domains contained within them. In addition to the diversity of particle shapes and morphologies that we see in the atmosphere, we also know that organic particulate matter could be semi-solid. So instead of a well-mixed particle, you can have something that's highly viscous and actually does not mix very easily. So as a cartoon to show you how this might affect heterogeneous oxidation, I have these three simplified cases here. On the left-hand side, I'm showing a low viscosity particle. In the middle, a semi-solid or solid particle, and then on the right, a coated or basic separated particle. And the shade of green that I'm showing kind of indicates the extent of oxidation. So, for example, a low viscosity particle that's well mixed will have a uniform, lightly oxidized composition. Something that's high viscosity and does not mix very easily, on the other hand, might have a very, very highly oxidized outer shell, but the inside of the particle, since it's protected from the OH radicals, won't be oxidized at all. And then something similar for the coated or phase separated particles, because you have this thin outer layer where the oxidation is confined to, you can get really high oxidation for that thin outer shell, but nothing's happening in the inner core. So one of the reasons we might care about this is that it's been shown, for example, that cloud condensation nuclear activity might be highly dependent on the surface composition and not the bulk composition of aerosol. But all the previous studies we've been looking at have really looked at kind of the average bulk composition of aerosol. So to try and probe this coated aerosol case, we did some flow tube experiments. So again, here we're using squalane. This is the structure of squalane, C30H62, and it's a highly branched saturated hydrocarbon. To generate these particles, we first atomize ammonium sulfate as like our inorganic seed particle, and then we pass that particle through a heated tube furnace that has a reservoir of squalane in it. And then as we change the temperature of the furnace, we can either condense more or less organic onto those particles. And we can also produce pure squalane particles by omitting the ammonium sulfate and just heating the squalane up to a higher temperature until it homogeneously nucleates, forming pure squalane particles. And then these particles go into the flow tube reactor. We add water, vapor, and ozone, so we can generate OH in the flow tube when we expose the tube to 254 nanometer light. And we also add isopentane. We're just using this as an OH tracer, so we can quantify how much OH we're generating in the flow tube. So we H the particles here, and then they go through an ozone scrubber to remove the ozone, and then we're measuring the chemical composition with an aerosol mass spectrometer. So when we take a look at the data, on the left, I'm showing the rate of squalane loss, or the squalane loss versus OH exposure. And what we see is for the coated experiments that the squalane loss is much, much faster. So each one of these different colors is for a different experiment. So these are 3 different coating thicknesses that I know. And then the black and the gray points are 2 pure squalane experiments. So you can see over the course of the experiment, we lose something like 40%, or we reacted away about 40% of the squalane in the particle for these pure squalane cases. For the coated particles, we've nearly lost all of the squalane. And I just want to point out here, this OH exposure of 5 × 10⁻11 is about approximately equal to about 4 days of aging in the atmosphere if we convert that based on average ambient OH concentration. What we can do from the data on the left is we can actually fit each of the separate experiments to an exponential to get your squalene decay rate. And then we can plot the squalene decay rate here on the x-axis on the right against the organic surface area to volume ratio. So what we see when we do this is that this enhancement in rate, when we're losing, this enhancement of rate for the loss of squalene is linearly dependent on the organic surface area to volume ratio. So this kind of makes sense. The rate at which you lose squalene is really dependent on the flux of radicals to the particle surface, and then the number of organic molecules in that particle. Now we can also look at the average composition for these particles. On the left, I'm showing the change in the average carbon oxidation state, and on the right, the fraction of carbon remaining in the particles. And then you can see, again, the pure particles show relatively slow changes in composition as they're aged over about 4 days of atmospheric aging time. And then the coated cases show much more rapid changes in chemical composition. So one interesting thing here is that the squalene decay rate showed a very linear, predictable and linear response based on the organic surface area to volume ratio. But in this case, things aren't as clear. So for the thickest coating, for example, we do see that change more slowly than the thin coatings, which we would expect. But then the 80 and 83C coating look very similar. And then when we look at the loss of carbon from these particles, they're kind of all overlapped with each other. But we do see very enhanced changes in composition for these thin coatings. But another way to look at this data, rather than looking at it in terms of OH exposure, is that we can actually look at it in terms of lifetimes. So lifetimes is oxidation lifetimes is basically any folding time based on how much squalene is remaining in the particle. So after one lifetime, the squalene concentration in the particle has decayed to 1/E of its initial concentration. And we plot the data in terms of lifetimes instead of OH exposure because that removes the effect of the physical properties of the aerosol, for example, the surface area to volume ratio. It kind of lets us compare all of these experiments on the same basis. So when we plot the data in this way, what we see is all the experiments kind of collapse onto one line. I've blown up this initial segment from 0 to 0.5 lifetimes, so you can see the data for the pure particles here. But essentially, it all pretty much looks the same. And what this means is that the rates in composition change are really driven by the organic surface area to volume ratio, and not any difference between the reaction products that are formed or any differences in chemical reactants or reaction mechanisms. Okay, so we have seen that these thin coatings can change very rapidly compared to pure particles. But squalene is a very unique molecule. It's not really representative of ambient organic aerosol, just like any one single precursor may not be representative of ambient organic aerosol. So what we did was we actually tried to figure out what our results meant for aging of ambient aerosol. So to do this, we took the randomizations I showed earlier from Kroll 2015. So that was the 10% loss of carbon over about a week and the 0.6 increase in carbon oxidation state. And we applied our enhancements based on the surface area to volume ratio to those results. So for example, the black lines in each of these plots is basically exactly what is in that Kroll 2015 parameterization. And I'm showing a variety of different coating thicknesses to compare to that. So essentially all of these particles have a total diameter of 200 nanometers. So for example, this 50 nanometer coating means you have a 100 nanometer core particle and then 50 nanometers on each side to give you a total 200 nanometer diameter. And then on the left panel, I'm showing the decay of some hypothetical tracer. So for example, if you're using levoglucosan as a tracer for biomass warming, for example, in the middle, I'm showing the average carbon oxidation state change. And on the right-hand side, I'm showing the fraction of carbon remaining in the particles. And what you can see is that for these very thick coatings that are about 50 nanometers or above, we don't really see any difference between the rate of change between the pure particle and then the coated particle. But once you get down to, say, the 20 nanometer coatings and below, especially 10 nanometers and below, you start to see very rapid enhancements for these composition changes. So whereas you may only lose, say, 10% of the carbon mass over the course of 10 days for these pure particles and the thickly coated particles, when you go down to much thinner coatings, you can really lose a substantial portion of the mass, so 50% or more for these thinner coatings. So the rate of the tracer loss, change in carbon oxidation state, and the carbon loss depends strongly on the coating thickness or the surface area to volume ratio of the particles. So to briefly conclude this section, the particle morphology, and in this case, organic surface area to volume ratio, is important for heterogeneous oxidation kinetics. We see that the composition of the thin coatings can change very rapidly, both in terms of carbon oxidation state and in terms of the carbon mass in the particle. But even though that we were looking at coated particles in this case, this has implications for pure organic particles that may mix slowly. So for these solid particles, you might be able to get some very rapid oxidation at the surface, whereas the core of the particle may remain unoxidized. So now we've seen how morphology can affect the heterogeneous oxidation kinetics. We wanted to dig a little bit deeper into the system and look at the products and reaction mechanisms that happen during heterogeneous oxidation. So because I'm going to be talking a little bit more about the molecular products from the system, we'll go a little bit deeper into the reaction mechanism and make it a little bit more complicated than I showed before. So we start with some organic molecule that I'm showing here as RH. Hydroxyl radical comes in and abstracts a proton from that, forming an alkyl radical, R. Typically what happens in the atmosphere is O2 will add to this alkyl radical, forming a peroxy radical, RO2. And then from there, the peroxy radical can do a couple of things. It can either form stable products from that stuff alone, and it will form some functionalized products there, or it can go on to form the alkoxy radical, RO. And that alkoxy radical is a little bit interesting because there are multiple pathways that can undergo. There are a few different reaction mechanisms that lead you to functionalized products, but this pathway the alkoxy radical can also give you fragmentation. So this is the way where you can actually lose mass from these particles. Some of the earlier work done in this area was actually done in John's lab. But if we take a look at if we can actually identify and quantify the products from heterogeneous oxidation, we can say something about which processes are important for heterogeneous oxidation of organic aerosol. The problem is that very few studies have actually quantified these products, even though there's been a few that have identified a handful of products from them. So with this new generation of aerosol mass spectrometers, it's a good opportunity to look at a wide range of products that come from these oxidation processes. So this experimental setup is very similar to what I showed for the flow tube experiments. The main difference here is that we've replaced the flow tube with the environmental chamber. So if you were at Chris Kappa's talk a few SOCAAR seminars ago, you might recognize this main chamber. This is what we built and took to Montana for the FireX campaign, and now lives in Jesse's lab. The nice thing about this chamber is that since it's so small, the experiments are actually quite fast. So, a typical meter or 10-meter chamber, you would typically run over the course of a full day. And it would take like 1 or 2 days to flush out, but in this case, our experiments are something like half an hour, 45 minutes. And then we can flush it out over the course of 1 or 2 hours and then run another experiment. Otherwise, again, we're coating squalene on ammonium sulfate. This isn't because we specifically want to look at the effects of coating thickness, but basically we're just using this as a technique so that we can correct the loss of particles to the chamber walls. Again, we have water vapor and ozone, so we can generate OH with the 254 nanometer lamps, and then we have our trusty aerosol mass spectrometer to measure the average chemical composition of the particles. But in this case, we also have 2 PTR3 mass specs. So these PTR3s are proton transfer reaction mass spectrometers. They're both time-of-flight instruments, and they've got a unique inlet and reaction chamber that allows for longer reaction times. So it will give you high sensitivities. One of the PTR3s we use to measure the gas phase composition. So this gives you specific gas phase compounds. And the other PTR3, we actually have a special inlet on it. So it's a particle phase inlet. It has a denuder, which strips out the gas phase compounds, and then it goes into a heated glass tube, which vaporizes the particles, so it can measure those molecules that were in the particle phase in the gas phase. So here are a couple plots that look probably very similar to what I showed previously. So I'm showing the squalene decay as a function of OH exposure on the left, and then the carbon mass in black, and the total organic mass over OH exposure in green. And one thing to note here is that we've really pushed the chemistry pretty far. So previously, we were only going out to a few days of oxidation, but here we're going out to more like a month of oxidation. So we're really trying to push the chemistry to see what products are formed and what happens kind of like at a later stage of oxidation for these particles. So under these conditions, we basically reacted all of the squalene from these particles away, and then we've lost something like 40% of the total organic mass and then 75% of the carbon mass from these particles. So the organic mass is dropping less than the carbon mass because you're also adding oxygen to these particles, which will contribute some mass to them. Because we have these two different reaction systems where we essentially run similar experiments, what I wanted to do is to compare to make sure there weren't any significant differences between the two reactors. So instead of showing the data in terms of OH exposure as I have on the left, we can convert that OH exposure to oxidation lifetimes. Again, this is so we can compare the different experiments, removing the effect of any physical properties of the aerosol, so we can more directly compare the two. And what we see is pretty encouraging. So the two experiments actually look very comparable. In the black are the data from the chamber experiments that I'm showing here on the left-hand side. And then in the dotted line is that fit from the flow tube coating experiments that I showed earlier. So, after two oxidation lifetimes, they both show about 30% or so carbon loss. We can do something similar with the average aerosol mass spectrometer elemental ratios. So on the left-hand side, this is the data from the chamber study. And what we see is the oxygen-carbon ratio increases pretty substantially from 0 to about 1. So, barring any effect of fragmentation, this would mean that, squalene goes from having 0 oxygens per carbon to 1 oxygen on every single carbon atom. And then you also get a concurrent loss of hydrogen from these particles. And then when we compare the change in oxidation state from the chamber in the solid blue line compared to flow tube experiment in the dashed line, we see that these slopes are very similar. There's only some difference in the initial change in the carbon oxidation state. So the initial increase for the chamber experiment seems significantly faster, and this might be because of the OH concentrations in the two different reactors. So in the flow tube reactor, we're running at very high OH concentrations. And then in the chamber, especially early in the chamber run, we have fairly low OH concentrations. So that might mean that the uptake of oxidants is more efficient for the low OH concentration case. And that may affect because you have different radical concentrations, that may affect the different branching ratios between the different reaction mechanisms. So that potentially might be a reason why you're getting faster oxidation initially for the chamber study. But overall, the flow tube and chamber studies look very comparable, which is good news. And what we want to do now that we have a good idea of what happens for the bulk composition of the aerosol is try and dive into what the molecular changes are for these experiments. So I said we have this PTR3 that's looking at species and gas-phase composition. And it can measure a wide variety of different organic compounds. But when we look at the mass spec, we're really only seeing two signals that really pop out. So the first one is the C3 compound C3H6O, and the other one is the C11H24O. And we can see is that these compounds show very different evolution over time. So the C3 compound grows in and then kind of levels off at higher aging times, whereas the C11 compound shows this really quick burst and then it decays away to nothing. And this data has been corrected for dilution in the chamber. But an alternative way to look at this is to actually plot it, instead of plotting it against the OH exposure, so the approximate amount of aging time, is to plot it against the amount of reactant consumed. So this technique comes from some older papers by Roger Atkinson. And what they do here is they fit the initial formation of the product versus the reactant consumed. So here I'm fitting just the first 4 points. And by doing this, if those first initial points are linear, that indicates that the product is a first generation product from the reactant. And you can also use this linear fit to extrapolate how much of the product is formed if there were no secondary OH reaction. So the reason why in the previous slide we were seeing this rapid decay of this compound and a small amount of decay for the C3 compound, because there's still OH in the chamber as these products are coming off the particles. So they're going to continue to react and then be depleted depending on the reaction rate constant. So what we can see here is for this C3 compound, if you compare the amount observed in the chamber at the end of the experiment compared to what we would predict if there were no secondary OH reaction, those look very comparable. So that's consistent with a compound like acetone, which has a very slow reaction rate constant with OH. But if we look at the C11 compound, you see this really wide discrepancy in the amount of the C11 compound that we expect to be formed versus what is observed in the chamber at the end of oxidation. And that's just because this compound reacts pretty rapidly with OH radicals. So even though you're not seeing any left in the chamber at the end of the experiment, you've actually formed a lot. It's just been reacted away. And this is consistent with the C11 compound being something like a C11 alcohol. So I'm going to tentatively assign this as undecanol. We also have the second PTR3 instrument looking at the particle phase. So if we're looking at the particle phase and we are seeing these fragmentation products in the gas phase, we should also see their co-fragmentation products remain in the particles. So if you're losing the C3 product to the gas phase, you should still be able to see some C27 compound in the particle phase. And indeed, we do see the 2 different C27 species in the particle phase PTR3. The first is a C27H54O, so we think that's a carbonyl C27 compound. And then we also see this C27H24 or H54, which is a bit of an unusual species, but we think that's actually an alcohol dehydration product. So because the particles are going through this heated inlet, you can get this alcohol dehydration where you lose water and you end up with this C27H54 compound. On the right-hand side, if we're losing C11, a C11 alcohol to the gas phase from the particles, there should be a remaining C19 species there. And we do see that C19H38O compound there as well. So we can see these co-fragmentation products in the particle phase using the PTR3 with the particle phase inlet. So with these species in mind and the acetone and undecanol identifications for these 2 species, we can draw some proposed reaction mechanisms. So for acetone, it's pretty simple. This is just the structure of squalene here. We have OH abstracting a hydrogen from this tertiary carbon. O2 adds forming the peroxy radical. And then once the alkoxy radical forms, then you can get this fragmentation next to that tertiary carbon. That leaves you with acetone and then the C27 radical, which can then go on and react to form the other species that I showed that were in the particle phase. For undecanol, it's a little bit more complicated. Again, we get, it's initiated by hydroxyl radical abstracting a hydrogen from a tertiary carbon here. And then you can lose this C19 species. So that C19 species we did see in the particle phase. And you're left with this alkyl radical. This alkyl radical can then form the peroxy radical, go on to form the alkoxy radical. And what this alkoxy radical can do here is, instead of fragment like we saw in the acetone case, is that alkoxy radical can also grab a hydrogen from a neighboring molecule. So if it does that, then you can form undecanol, the C11 alcohol that I've showed. Now, I also mentioned that one of the reasons why we want to use PTR3 is because we can see such a wide diversity of molecules in the gas phase. But there were really only 2 that popped out, the undecanol and the acetone. However, we do see many, many other small species, and once you add all those small species up, that actually adds up to an appreciable amount of mass. So there's something like 100 or so ions that we can identify and give molecular formulas to. And when you add all those up, it's actually quite a bit of mass. So when we start the oxidation, we see a burst of gas phase carbon, and I've just labeled the undecanol and acetone here. And those two species alone seem to account for about 50% of the gas phase carbon that we're observing. But if you add everything else up, there's another 50% of carbon mass hidden in all of these small species. Some of these larger slivers of mass that we're seeing are from C6 and C8 compounds. So if you look at the structure of squalane, you can see some natural fragmentation points. So basically wherever there's a tertiary carbon next to that tertiary carbon, you're more likely to get fragmentation. So at that C3 point, the C6 point, C8, C11. So you can see that these two compounds account for about 50% in the beginning, and then at the end, as the oxidation continues, it's really dominated by acetone. But this data is only corrected for dilution. It's not corrected for the secondary OH reaction that I had shown previously for the two acetone and undecanol species. So instead of correcting each single ion separately like we did for acetone and undecanol, we can actually just try and do it for the total gas phase carbon. So if we take that total gas phase carbon that we observe in the chamber, dilution corrected, and then fit the initial formation versus the loss of squalane, we can get a corrected amount of gas phase carbon, assuming no secondary OH reaction. So when we do this, we see that we seem to be forming something like 35 micrograms of carbon in the gas phase. And this accounts for about 50% of the carbon that we see lost from the particle phase. So it looks like we can actually account for a good chunk of the carbon that's being lost from the particles in the gas phase once we add up all the different species that we're seeing, including all of those small signals. So what we saw for the squalane oxidation was that acetone and undecanol were formed in high yields from squalane oxidation, and this is coming specifically from alkoxy radical fragmentation. We can account for about half of the mass lost from the particle phase in the gas phase, adding up all the small signals. And then heterogeneous oxidation could be a significant source of oxygenated VOCs over longer aging times. Okay, so I'm going to switch gears a little bit and move to the indoor world. And we're going to look at what volatile products are formed from the heterogeneous ozonolysis of third-hand tobacco smoke. So when we think of cigarette burning indoors, cigarette burning emits both particles and gases. So we see particulate matter, but also gases such as formaldehyde, nicotine, benzene, and polyaromatic hydrocarbons. One thing that's unique about the indoor environment is that the indoor environment has a really high surface area to volume ratio compared to the outdoors. So because there's so much surface area indoors, a lot of these products are going to partition to surfaces. So they get partitioned into surfaces such as walls, furniture, clothing, and dust, etc. These compounds that partition to these surfaces, so this tobacco smoke residue on these indoor surfaces, can also partition back to the gas phase. So it can slowly desorb off the surface back to the gas phase. And this combination of the compounds that are on the surface and the semi-volatile material that's going back and forth from the gas phase to the surfaces is referred to as third-hand smoke. So this third-hand smoke can actually partition to ambient particulate matter. So Pete DiCarlo and Doug Collins, studies by them have both shown that third-hand smoke can partition to particles indoors, and it can be a route of exposure that way through human inhalation. Not only that, but that the composition of the particulate matter matters for which compounds will partition to them. So for example, acidic particles are more likely to uptake reduced nitrogen species from this third-hand smoke, but compounds that are mostly made up of carbon and hydrogen are mostly more likely to partition to hydrocarbon-like aerosol. So not only can these species partition back and forth between surfaces and the gas phase and particulate matter, but because they live on surfaces for so long, there's ample time for oxidation to happen. So indoors, The main oxidants that we're thinking about usually are ozone, HOCl from, like, say, bleach washing, nitrous acid, and in certain cases OH as well. But I'm going to be focusing on the ozonolysis of these third-hand smoke species. There have been a couple previous studies on heterogeneous oxidation related to third-hand smoke, but most of them have been done on a single pure compound, so nicotine. So nicotine is a well-known major component of cigarette burning. And on the left-hand side, I'm showing a schematic from Slayman et al. This is from a group out at LBNL. And what they've shown is that HONO, nitrous acid, can actually react with nicotine on surfaces to form tobacco-specific nitrosamines. So these are well-known carcinogenic compounds. They've also done, like, indoor or swipes of a cigarette smoker's card to determine that these are actually observed in the real world as well. On the right-hand side, I'm showing a plot of the loss of nicotine off of a Teflon surface from the same group out at LBNL. So with just clean air flowing over the surface, you see a significant amount of desorption of nicotine from the Teflon. This is because nicotine has a fairly high vapor pressure. But then if you add ozone to the mix, then you get a much more rapid depletion of nicotine off of that surface, indicating that there's some amount of heterogeneous oxidation potentially happening. And we also observe some new products such as formaldehyde forming in the gas phase. So there's been a couple of studies like this, but most of these studies have not looked at the complex mixture of third-hand smoke. Instead, they've only looked at very simple compounds such as just nicotine. So what we wanted to do was look at the complex third-hand smoke mixture, look at what compounds are volatilized from the smoke deposit onto surfaces, try to figure out what the major gas phase products are formed during heterogeneous ozonolysis, and also find out if there are any differences in the yields from these products when they're deposited on different types of indoor surfaces and if relatively place angle or not. So this is how we coat our indoor materials. We're using 3 different kind of proxy indoor materials. The first is just glass. We're also using a painted glass that's painted with the indoor enamel paint, and also a piece of cotton canvas. So what we do is we first light the cigarette, place it in the cigarette holder. That's just this right here. And then we take a couple puffs using a pump. This line is connected to a pump right here. And then we have clean air that flows the cigarette smoke through the coating chamber where the indoor surface of interest is to be coated. So we coat with a couple puffs, cap that off, let the smoke deposit onto the surface for about 20 minutes or so, and then we just do the same thing on the other side of the surface to ensure even coating. And then when we actually do our oxidation experiments, before we oxidize them, in order to focus on the compounds that are really long-lasting and lingering that would last for a long time indoors, we actually flush them overnight. So we take that surface, place it in a flow tube, and then just flush clean air over it overnight to remove the most volatile components. Once we flush the surface, we place it in a reaction flow tube where we can add ozone from a Penray lamp and then water vapor to control the humidity. And then we're measuring the species with an acetate ion time-of-flight chemical ionization mass spectrometer. So if you're not familiar with the acetate top SIMS, this is basically a way to measure gas phase acids. Specifically, anything that is more acidic than acetic acid is going to detect. So just briefly, before we actually do any oxidation, we just want to see what is coming off of the third-hand smoke surface as measured by the acetate time-of-flight mass spectrometer. And we see a variety of acids. So we see nitrous acid, isocyanic acid, formic acid, acrylic acid, and nitric acid, as well as some small signals from some other compounds. And the inset here shows just the first few minutes of desorption, where the main panel shows it over the course of a few hours. And what you see is that, you see a very fast desorption, which just indicates the headspace of the reactor being flushed out. And then you see a slower desorption, which corresponds to the slow desorption of compounds off of that third-hand smoke surface. And the major thing to make of note here is that even after many hours of flushing, that there's still compounds coming off of the third-hand smoke surface. So it's very persistent. Then we move towards an oxidation experiment. I'll I'll just walk you through this, showing the isocyanic concentration or signal on the left, on the y-axis, the time on the x. We insert our third-hand smoke coated glass here at this point. You can see it kind of flushes out the headspace of the reactor, and you're left with some steady-state concentration of HNCO. And then once that has reached steady state, then we turn our ozone pen ray lamp on, and then the HNCO signal increases. We go back to a bypass just to check the background of our instrument, and then we can do a variety of other ozone concentrations. And we can see that roughly the HNCO signal is proportional to the amount of ozone that we're adding to the reactor. We can put all these results together, and here I'm showing the HNCO formed concentration on the y-axis versus the amount of ozone reacted. And you can see that the HNCO form shows a linear relationship with ozone concentration, and the humid and dry conditions look very, very similar. We can move to some of the other surfaces. So if we take a look at the formation on painted glass, that yield actually drops substantially. So if I'll just switch back for a second. So we're seeing maybe 35, maximum 35 PBT formation here for the plain glass sample. But under the painted glass sample, we're seeing about half of that formation. And under this case, for some reason, the humid condition is showing lower HNCO enhancement with O3 compared to the dry condition. And then finally, we can move toward the cotton canvas. So the cotton canvas is quite a bit different. It actually shows very, very small amounts of HNCO formation. This, very small amount is comparable to what we see in our blank. So we're essentially not seeing any HNCO formation when we deposit the smoke onto cotton canvas for some reason. And the differences between the yields for the different surfaces aren't very clear yet, but it might have something to do with the surface composition, how much water may be on the surface, or the surface acidity, or something like that. So just to conclude this project, we saw small gas phase acids when ozone is added to the third-hand smoke samples. HNCO shows the clearest enhancement, although we also see enhancements of things like colonel and formic acid. The indoor material does seem to matter. So the third-hand, the HNCO off of glass shows the highest yields, whereas on canvas it shows basically zero formation. And relative humidity doesn't seem to play a large role for these oxidation experiments. Okay, so I'll just wrap up the entire presentation now. Heterogeneous oxidation can change the surface composition rapidly from hours to days. Over longer aging times, it seems like heterogeneous oxidation can be a good source for oxygenated volatile organic compounds. And also, aging leads to the emission of additional compounds from third-hand to smoke. And I'd just like to thank my previous group at MIT, so Jesse Kroll's group. None of these people exist in the group anymore except for Jesse. And then this is a more recent picture from John Abbott's group, and only 2 people are missing now here. I'd also like to thank the funding sources, so NSF and the Alfred Sloan Foundation.